Alright, so in this problem we have a mass system which has a rotating eccentricity on it, and we're asked to find the equation of motion for this system in terms of the coordinate x, given a little bit of information about the orientation of the imbalance and some parameters in the system. And so the way I'm going to do this is I'm going to start by recognizing that I'm going to use Newton's second law to solve this, and so I'm going to try to draw a separate free body diagram for each object, which in this case will be one for the particle. And in the case of the particle, I know I can have some force here, let's just call it F, that it's going to create. And we know that that's going to have some mass times acceleration, and you can write this in a number of coordinate sets if you'd like. I'm going to just choose to do so in the ij coordinate set, and so if I do that, what I'm going to get here is I'll simply call it m times the acceleration of the particle in the x, and in the vertical direction I'll have m times the acceleration of the particle in the y. And I know that by definition, let's see here, that this angle right here is the angle theta. And then I can also draw a free body diagram for my block, and if I do that, in this case I know that the block is going to have a mass times acceleration to the right, which I will call mx double dot. And if it moves positive to the right, I'll have a restoring force pushing back of 2kx and one pulling back of kx. And I will also have potentially normal forces between the ground and the contact, and also the mass of this big block acting down mg. And of course I forgot the effect of gravity on the particle up above too, so we can have a little mg acting there. Okay, so now that I have those, I can take these two free body diagrams and make some equations of motion here. And the way I'm going to do that is, first of all, I'm going to sum forces in the x direction on the big block. And if I do that, what I'm going to get is that this is equal to m times x double dot. And so if I go ahead and make the substitution here, I'm going to have minus kx minus 2kx. And actually, I forgot a force. I forgot to put back in my equal and opposite force from the particle, little f, big F here. So I'm going to have plus f times the cosine of theta is equal to m times x double dot. Now clearly I still have this force from the rotating imbalance in here, so I'm going to need to figure out what that is. And the way I'm going to do that is I'll now look at the particle. And if I look at the particle and I do this in the x direction, I can sum forces in the x and set that equal to m times apx. And if I look at the x direction forces on this particle, I'm going to have minus f times the cosine of the angle theta is going to equal the mass of the particle times its acceleration in the x. If I go ahead and call this equation 1 and equation 2, I realize that I have two equations here with a few too many unknowns. In particular, I still have the dynamic variable x and its derivatives as unknowns, f is an unknown, and also apx is an unknown. And so the way I'm going to solve this problem is I'm going to go ahead now and do a little kinematics and find what apx is. And so to do that, I can say the acceleration of point P is going to equal the acceleration of point O, plus, in this case, alpha, which that particle is spinning around, cross r of p with respect to O, minus omega squared times r of p with respect to O. Now in this case, we can go ahead and we're given the information here that essentially omega is a constant, and so if I plug this in, this is going to give me, well, the acceleration of point O is x double dot in the I. Alpha essentially goes to 0, so this is going to go away, and I'll have minus omega squared times the position vector of p with respect to O, which is going to be e times cosine of omega t in the I, plus e times the sine of omega t in the j. If I now take just the x component of this, I'm going to get that apx is going to equal x double dot minus omega squared e times the cosine of omega t. We can call this equation 3. Now if I look at these equations, what I have now is I have as many equations as I do unknown, and so I can start to plug them all in together. So if I take the result of 2 and plug it into 1, I'm going to get minus 3k times x minus m times apx is equal to m times x double dot. And then if I substitute in apx here, I'm going to have minus 3kx minus m times x double dot plus m omega squared e times the cosine of omega t is equal to m x double dot. I can then take this equation and write it in standard form, and that's going to give me quantity m plus m times x double dot plus 3 times k times x is equal to ln omega squared e times the cosine of omega t. That is the equation of motion for this system. Now if I want to solve this equation and find the steady state response x of t, the way I'm going to do that is through the method of assumed solution. So in this case, what I can say is that the particular solution x sub p of t is going to be given by some known unknown a times the cosine of omega t plus some unknown b times the sine of omega t. I can take two derivatives of that and I'll get that xp double dot of t is going to equal, in this case, minus a omega squared times the cosine of omega t minus b omega squared times the sine of omega t. And I can take both of those two results and plug them back into the differential equation of motion. If I do that, what I'm going to get is that quantity m plus little m times x double dot, which is minus a omega squared times the cosine of omega t, minus b omega squared times the sine of omega t, plus 3 times k times x, which is a cosine omega t, plus b sine omega t, is equal to m times omega squared times e times the cosine of omega t. I can then retain like terms. If I pull out things multiplying cosine omega t, I'm going to have m plus m times minus a omega squared plus 3 times k times a is equal to m omega squared e. And if I pull out terms multiplying sine of omega t, I'm going to get minus quantity m plus m times b omega squared plus 3 times k times capital B is equal to 0. If I solve the first equation here, I'm going to get that a is equal to m times omega squared times e divided by 3k minus quantity m plus m times omega squared. And if I solve the second equation, I'll get b is equal to 0. This means that the particular solution to this equation, x sub p of t, will be given by m omega squared times e divided by 3k minus quantity m plus m omega squared times the cosine of omega t. Alright, I think that just about wraps up this problem. I'll go ahead and leave the rest for you to work through and wish you the best of luck. Take care.